Hi everyone, this is Professor Muldrow, and in this video I'm going to show you several techniques for sorting elements in a list. Now what you're looking at is a PowerPoint presentation that I have put into Canvas. You need to go to the Files area, go to the PowerPoints folder, and look in the Goodrich folder. That's where you'll find this PowerPoint presentation. In this video, I'm going to show you the non-recursive sorting techniques. There are 3 of them. There's a total of 5 sorting techniques in this PowerPoint presentation, but I'm only going to focus on the first 3 in this video. These are the 3 that do not involve recursion. The first one is called a bubble sort. In a bubble sort, here's what happens. A bubble sort moves smaller elements toward the start of the array and larger elements toward the end of the array. It does this by comparing pairs of elements. Now, in order to do this, you must go through the array. For the number of times you go through the array is the number of elements. So for each pass through the array, here's what you do. Each pair of successive elements is compared. That means 2 elements right next to each other are compared. If the first element of the current pair is larger than the second element, those elements are swapped. Otherwise, the 2 elements remain where they are. Now, furthermore, it says for the first pass, the first time you go through the array, the entire array is considered. For the second pass, the second time you go through array, all but the last element is considered. So you consider all but the last element in the list and so on. By the way, forgive me if I say array when I should say list. It's an old habit. Here's an example of how a bubble sort will work. Now, this picture does not totally complete the bubble sort, but if I go through this, I believe you will get the idea. All right, so here on our first try through the array, this is the first column. We first compare these 2 elements, and we see that the first element is larger than the second, so we swap them. You notice the 10 now and the 29 swap places. Now we compare these 2 elements with that swap being finished. And once again, first element larger than second element, so the 29 and 14 swap places. Now we compare these 2. As it turns out, 29 is less than 37, so we don't do a swap here. But now we come here and we see for these elements, 37 is larger than 13. So the 13 goes there, the 37 goes there. So we have finished the first pass through this list. And as it turns out, 37, which is our largest element, is all the way to the right. It's now the last element. So in this second column, we're going to start this whole process over again. But this time, we're only going to go up to the 13. The 37 has already been sorted, so we're going to ignore it. So we compare these 2 elements, and the 10 is less than the 14, so no swap there. Then we compare these 2 elements, and the 14 is less than the 29, so no swap there as well. Finally, compare these 2 elements, and we have the 29 larger than the 13. 29 goes there, 13 goes there. And we have now finished the second pass through the list. And you'll notice 29 is now in its rightful position. So we will do this one more time. We will go through the array at least once more, but we're only going to compare up to these elements. We're going to leave out the last 2 since they've been sorted. That is how a bubble sort works. It will bubble up the smaller elements to the top, and the larger elements bubble down to the bottom. Hence the name bubble. The next type of non-recursive sort is this one, a selection sort. This is probably the most common sort that you will see examples of in computer science textbooks. Here's how it works. Selection sort finds the smallest element in an unsorted array and moves that element to the beginning of the unsorted array until the array is completely sorted. For each pass through the array, this is what takes place. The smallest element of the unsorted array is found, and this element changes places or gets swapped with the first element in the unsorted array. Now, of course, you might be thinking, oh, what do you mean by the unsorted array? Well, here's what that means. For the first pass, the first time through the list of the array, the unsorted array is the entire array. That's the whole array. The second time through, the unsorted array consists of the second through last element. So the second time you go through an array, you don't worry about the first element. That's the smallest. It's already been sorted. Now you start at the second element and go through the end of the array or list and find out where the smallest element is and swap that, etc., and so on. So here's an example. Suppose this is our array to start with, right here. Okay. This is the first time through, so we're going to assume that the unsorted array is the entire array or unsorted list. So we start by assuming that the first element of the unsorted array, in this case, the first element of the array, is the smallest one. We compare all the other elements to see who is actually smallest. Well, it turns out the smallest element in this list is the 1 right here. So what happens is the 1 and the 8 will swap positions. And that's the first time through the array. Now, for the second time through the array, the unsorted portion is going to be in the red box. It's just this. We do not include the 1 in the unsorted portion of the array because it's already been sorted. We determined it's the smallest, so it's already in its rightful place. We just have to determine who comes after the 1. So again, we'll assume that the first element of the unsorted array, that's this 5, which is at index 1, is currently the smallest. And we compare all other elements in the unsorted portion of the array to see if anyone's smaller. Well, it turns out there's a 3. That's the new smallest element. So the 3 and the 5 swap places. And now we have the 1 and the 3 in the correct place. One more time. Now the third time through the array, the unsorted portion is going to be in the green box. That's this portion right here. So we'll assume the first element of the unsorted portion, this 7, is the smallest. See if we can find a smaller one. Turns out the smallest element is this 5. That means the 5 and the 7 swap places. And I believe you can follow the rest of this to see that you eventually get a perfectly sorted list. That is how a selection sort is supposed to work. The last type of non-recursive sort we'll look at is called an insertion sort. This one has elements changing positions, but it doesn't exactly do a swap. Here's what we mean. An insertion sort finds the proper position for each element of an array on each pass, rather than just swap. To do this, the array is considered to have 2 subarrays. 2 subarrays. A sorted subarray and an unsorted subarray. Now here's what's important. For the first pass, first time through the array, the sorted subarray is the first element. First pass, sorted subarray is the first element, and the unsorted subarray is the rest of the array. Second pass, the sorted subarray is the first 2 elements of the array, and so on. Each pass inserts the first element of the unsorted subarray into its proper place in the sorted subarray. Makes perfect sense, doesn't it? Let's dig a little further. So here is the algorithm, the way you approach this. First thing you do is the first element of the unsorted subarray is compared to the last element of the sorted subarray. If the first element of the unsorted subarray is larger, that element is not moved. If the first element of the unsorted subarray is smaller, compare it to other values in the sorted subarray to find its proper place. So here's an example. We're going to try and run through this. Okay. So as it said on the previous slide, for the first time through, first pass, the sorted subarray is the first element of the array, and the unsorted subarray is the rest of it. Okay? So that means the 8 is our unsorted subarray, and 5, which is in green, is unsorted. The rest of this is unsorted right here. So we'll take this first element, just the 5, and compare it to the 8. Well, it turns out 5 is less than the 8. So therefore, we need to insert the 5 in front of the 8. Now that looks like a swap, but it really isn't, because now let's look at the next pass. So now we have our sorted subarray is this one in blue, which is the 5 and the 8. And here is the unsorted portion of the subarray in green. The first element of the unsorted portion is a 7. So we will compare it to the 5. Well, it is not less than the 5, so it doesn't go there. But it is less than the 8. So once again, it looks like you're swapping the 8 and the 7, but that's really not what's going on. What you need to do is you need to insert this 7 before the 8 and then remove it from where it was. So first you want to do something to insert that 7 before the 8. And then once that's done, remove the 7 from where it has been in the array or list. Okay. Now then, for the next pass, see what's happening here. Next pass, here is your sorted portion. Here is your unsorted portion. Look at this. The first element of the unsorted portion is the 1. So we compare that to the 5, and it turns out 1 is less than the 5. But notice, the 1 and the 5 don't switch positions. The 1 now moves in front of the 5. So this third time through the array, this really demonstrates what we mean by inserting. Notice in the next line, the 1 and the 5 didn't just switch positions. They didn't swap. We just moved the 1 in front of the 5. The 5 just got moved down one place in the array, along with everything else in the sorted portion. That's why I say for an insertion sort, what you need to do is when you find out where this element needs to go, you insert it into the array, and then you remove where it was. That is how you do an insertion sort. Now, if you're thinking, Professor, when do we see the Python code for doing these types of sorts? Well, you're not going to. I've given you an idea of how these work. Now you have to use one of these in the extra credit assignment. If you have any questions, please send me an email at kmuldrow@lbcc.edu.